Can you see my screen?
Yes. Yes.
I can see only 28 members. Can we start?
Yes, we can.
Yeah. So in the last class, we have seen about the classification of materials based on rheological properties. Can somebody record the class so that it may be useful for other members to go through? Is anyone recording? Yeah, somebody started recording. Now I think we are good to go. Hope everybody is able to see my screen.
Can't
Please
see.
confirm.
At the moment, we can't see.
Oh, let me share.
It's okay. It's okay now.
No.
It's
No.
okay now.
Okay. So we are going for the study of viscometers. So viscometers are nothing but the instruments or the equipment that are used for the measurement of viscosity. Viscometers are divided into two categories: single point viscometers and multiple point viscometers. Single point indicates, you're able to see even what I am writing on the slide, right?
Yes.
So single point indicates we can operate the equipment or the instrument only at one particular shear stress. You won't be able to change the amount of shear that is acting on the system. Generally, to plot the rheogram, we take shear stress on x-axis and rate of shear on y-axis, isn't it? So we start with the zero shear and gradually we increase the shear stress, and whatever the deformation that is happening in the system, we take on the y-axis. So single point viscometers, they won't be able to change the shear stress that is acting on the system. Can we measure viscosity without changing the shear stress?
Yes.
How? Please, everybody mute your mics. Thank you. Yeah, somebody told yes. May I know the answer? How can you measure viscosity without changing the shear stress? Somebody told yes just now, isn't it?
We can try to measure sedimentation through
Sedimentation is entirely different from, we are measuring the viscosity of solutions. Now you see, when it is a solution, because you have to measure viscosity for the liquids. Maybe it is water, or maybe it is glycerin, or maybe it is liquid paraffin, or maybe it is some castor oil. So we are trying to measure the viscosity of liquids here. So you have two types of viscometers: single point viscometers and multiple point viscometers. Single point viscometers clearly indicate that they get operated only at one particular value of shear stress. You cannot decrease the value, you cannot increase the value. So this is going to have only one particular fixed value of shear stress. Single point. The viscosity is measured at only one particular point of shear stress. Now my question is it possible to measure viscosity without changing the shear stress? Is it possible?
Yes, yes.
Yes. Yes, it is possible. Can anyone explain? Okay. Now we go back to the last class. We have seen about two different types of systems according to the rheological behavior. The first type of system is called as Newtonian system, and the second type of system is called as non-Newtonian system. Now, can anyone tell me the two important properties of Newtonian systems?
Directly proportional.
Yeah, no. Complete the sentence. Shear stress is directly proportional to rate of shear. Second point.
Is about viscosity.
Yeah, what is the point about viscosity? What is the statement?
In a Newtonian system, the viscosity is a constant property.
Exactly. So now you see here, you calculate viscosity at some x value, or you calculate viscosity at some y value of shear stress, or you calculate viscosity at some z value of shear stress. Will there be any change in viscosity?
It is constant.
Exactly. So you
There's
calculate.
no change.
Yeah, you calculate it, whatever may be the shear stress that you are applying, the viscosity is going to be constant. Yes, by using even a single value of shear stress. A single value of shear stress, you can measure viscosity. So single point viscometers use only one particular value of shear stress. Multiple point viscometers, we have a facility of increasing and decreasing the shear stress. We start with 0, we can go on increasing the shear stress. You don't have that facility in single point viscometers. Am I clear? What do you mean by single point viscometers and multiple point viscometers? I can repeat.
Yes.
Single point viscometers are used to measure the viscosity only at one particular fixed value of shear stress. Whereas multiple point viscometers, you can increase the force that you are applying, and you can even go for decrease in the shear stress that you are applying onto the system. So you have a facility of changing the amount of shear stress acting on the system. Now, can anyone tell me, single point viscometers are used to measure the viscosity of single point viscometers are used to measure the viscosity of Newtonian systems. Exactly.
Newtonian system.
So because, yes, Newtonian systems doesn't show any change in viscosity. Either you increase shear stress or you decrease shear stress. Viscosity remains constant. There is no need for us to measure viscosity at 0, at 1, at 10, at 100, and at 50. Wherever you measure, the viscosity is going to be constant. There is no change in the viscosity. So that is the reason single point viscometers can be used to measure the viscosity of Newtonian systems. Can we measure the viscosity of non-Newtonian systems by using single point viscometers?
No.
No.
Exactly, because non-Newtonian systems will have a change in viscosity the moment you change in shear stress. So they require what is happening to viscosity when you are increasing the shear or when you are decreasing the shear. So single point viscometers are not suitable for non-Newtonian systems. So when it is a non-Newtonian system, we need to go for multiple point viscometers. Hope I am clear.
Yes.
Yes, Prof.
So now everybody tell me single point viscometers are used to measure the viscosity of
Newtonian.
Newtonian systems.
Newtonian system.
And now the second question. Multiple point viscometers are used for the measurement of viscosities of
Non-Newtonian.
Non-Newtonian system.
Non-Newtonian systems.
I'm repeating my question. Multiple point viscometers are used for the measurement of viscosities of
Non-Newtonian systems.
I'm expecting a refined answer.
Non-Newtonian system.
Non-Newtonian.
I'm expecting a refined answer. They can be used to measure the viscosities of both. They can be used to measure the viscosities of Newtonian systems and also non-Newtonian systems, isn't it?
Yes, yes.
Yes. Yes, yes.
Yes.
You can measure the viscosity of Newtonian system at single point, or you can even measure at multiple point. There is no change.
Yes. Yes.
Single point can be used for only Newtonian systems. Multiple point viscometers are used for both Newtonian and non-Newtonian systems. So now we are going to look at two examples for the single point viscometers and two examples for the multiple point viscometers. Am I clear? And also we are going to look at the equations that are used to measure the viscosity by when you are using that particular equipment. Am I clear with this classification of viscometers?
Yes, Prof.
Yes.
Everyone. Is there any need to
Yes.
repeat or I brief it again?
Continue.
Okay. So we are going to look at two different types of single point viscometers and two different types of multiple point viscometer. In single point viscometer, the first one is the capillary viscometer. You can see the capillary viscometer. I'm just waiting for the slide to be moved. Are you able to see the picture?
Yes.
Can see
So
the picture.
this,
No. You can.
yes.
Yes,
You
you
can
are seeing
see
the capillary.
exactly.
Yes.
So this is a simple
Okay.
U-shaped glass tube. So you can see this U-shaped glass tube with two bulbs. You can see the first bulb, bulb 1 and bulb 2. A simple U-shaped glass tube. It's a glass tube which is transparent. You can visualize what is happening inside the tube. It will have each bulb on each arm of the tube. And on the right hand side, below the bulb 2, this is bulb 2. Below the bulb 2, we can see a narrow capillary arranged. Are you able to see that?
Yes, Prof.
Yes.
Yes. So now this is the construction of this capillary rise viscometer. It's a simple U-shaped glass tube that is transparent. We can visualize the movement of the liquid inside the glass tube. It is provided with one bulb on each arm. On the left-hand side, we can call it as bulb 1. And on the right-hand side, we can call it as bulb 2. Below bulb 2, there is an arrangement of a narrow capillary. And above that capillary, you can see two markings. Let us consider the markings as A and B. The markings are present. The first one above the bulb and second one above the capillary, below the bulb and above the capillary. Are you able to see those two markings, A and B?
Yes.
Yes.
What is the construction of this capillary viscometer? Can we move with the working? Can we go ahead with the working of the capillary rise viscometer?
Yes.
Yes, Prof.
So now the liquid whose viscosity we want to measure is added to this glass tube. Let us consider I added some volume of liquid to this glass tube. So the liquid is present all in this area. Now I am going to use a suction bulb. When the suction bulb is used, the liquid is sucked into the second bulb because we are creating a vacuum. We are creating a vacuum by applying vacuum to the suction bulb. So the liquid level starts raising to the level A. We make sure the liquid level is slightly above level A. We apply suction until the liquid comes slightly above the level A. So this is called as level A. Now we made the liquid to come slightly above the level A. If we don't apply this vacuum, the level will not raise in the second arm. So to raise the liquid above this level A, we are going to apply suction by using the vacuum pump. Now the actual experiment starts. Now we remove suction. What happens when we remove suction? What happens when we remove suction?
It's restored to the original
It
level.
goes down.
The
Level.
liquid starts dropping slowly.
Yes, the liquid will start dropping down. Now we are going to measure the time taken by the liquid to fall from A to B. Now we wait until the liquid reaches the level A. Now we are going to measure the time taken by the liquid to fall from A to B. So when the liquid is falling from A to B, the liquid is passing through the narrow capillary, isn't it?
Yes.
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 So viscosity of the liquid plays an important role when the liquid is passing through the capillary. When the liquid is dilute, liquid passes. When the liquid is dilute, liquid passes quickly.
Yes.
When the liquid is thick,
Passes
it
slowly.
will take more time to pass from the level A to level B. So that is the simple principle involved in the measurement of viscosity by using capillary raise viscometer. So definitely when viscosity is there, so that is going to resist the flow. More viscosity, more resistance to flow. The liquid flow between A to B is dependent on the viscosity. More viscosity,
Winnie.
more time to pass.
Kuja kusongea friend asome.
Less viscosity, less time to pass. Am I clear about the principle involved in Oswald viscometer? Sorry, this is capillary raise viscometer. The commercial name given for the capillary raise viscometer is Ostwald viscometer. I'll explain even that. Am I clear about the principle?
Yes, Prof.
So that is called as capillary raise viscometer.
Excuse, Doc.
Yes.
Prof.
Yes.
That is clear. Apart from, I've not gotten, where will we add this liquid whose viscosity we are measuring to?
No. You are going to measure the time.
The time.
Yeah. Now we are going to use this time to measure the
Yes.
viscosity. I'll tell you. Now I'm just
Yes.
confirming whether you got the principle. How are we measuring the viscosity or not?
Yeah, I got it, but I didn't understand how the liquid found itself inside the viscometer.
No, we add a liquid before starting the suction. We add a liquid. I told you we add liquid so that the liquid is filled here. You didn't observe this marking. We added liquid to the tube so that initially it will maintain its level like this, equilibrium level. Now we want the liquid to pass between A and B. To pass from A to B, definitely we need to suck the liquid so that it comes above the level A. Once it reaches A, now we start measuring the time. We start counting the time. How much time is it taking to fall from A to B? Definitely the time taken by the liquid to fall between A and B is dependent on its viscosity. If the liquid is thick, it will take more time to pass through the capillary present below the level B. If the liquid is thin or dilute, it will easily pass through the capillary and it will take less time to pass between A and B. Am I clear?
Correct. Yes, Prof.
The one who asked me the doubt. Am I clear now?
Yeah, Doc,
Yes,
you're
Prof.
clear.
Yeah.
So
now,
just a minute. There's something I'm not understanding. When the liquid we were adding through this other opening,
exactly
the one
from
opposite the sanction bulb.
yes, you can
Okay,
see the
thanks.
aroma now. We can
Okay,
add from
thanks.
here and we can add from the other end. From anywhere we can add.
Okay,
But
okay.
we apply suction from the right hand side arm because the level markings are present on the right hand side arm. So we are
Okay.
applying suction from this side.
Okay. Clear.
Okay.
Okay,
Yeah.
clear. Thank you.
So now this is going to work on the principle of Poiseuille's law. So which says the time taken by the liquid is inversely proportional to the viscosity. Sorry, it is directly proportional to the viscosity. More viscosity, more time, less viscosity, less time. So what are we going to do to measure the viscosity here is first we measure the time taken by water to fall between A and B. We maintain the conditions and everything standard. And we initially take water, we conduct the experiment, we'll note down the time taken by water to fall down between A and B. Now we are going to, water is considered as the reference liquid. In all the measurements of viscosity, we are going to use one reference liquid because of easy availability and because of economity of the water. We are going to use that as the reference.
Kama kuna amtel 45 kwa system ya A&E, kwa stock za A&E, ukipata iko, vanhu pena
Kindly
account
mute-
uniambie
kindly
daktari
mute.
animbilie, then you dispense.
Please mute your mics.
Kindly mute.
Amtel 45. Ndio sasa nione vile itafungwa hiyo
The leader,
account.
please mute.
Thank you. So we are going to use water as the reference liquid. We are going to
Hiyo swali
first
nauliza
add,
ni rahisi,
please somebody mute her.
kwani sijajimute?
Someone call.
Somebody please mute
Okay.
Faith. Done. Yeah, we are going to use water as the reference liquid. We are going to conduct the experiment by using water first. We add water to the tube. We suck water above the level of A. Now we slowly allow water to come to the level of A. And now we start measuring the time taken by water to fall down from A to B. So that we are going to note down as T1. Next, we are going to repeat the experiment. We remove water. Now we use the same viscometer to measure the time taken by the test liquid to fall down from A to B. We note down its time as T2. We are going to repeat the experiment first by using the reference liquid, which is water. The second trial, we are going to use the test liquid whose viscosity we want to measure. We note down the time taken by water as T1. We note down the time taken by the test liquid as T2. Now we are going to use the formula neta 1 over neta 2 is equal to rho 1 T1 over rho 2 T2. So this is a comparative measurement of viscosity. We are comparing the viscosity with respect to the time taken by the liquids to fall between the given markings. Neta 1 is the viscosity of water. We already know that. Rho 1 is the density of water. T1 is
Time one.
Time.
taken by water.
what is time 1?
Time taken by
Time
water.
Taken by water to
To
fall
the
fall
water.
from
from
A
A to B.
to B.
Time taken
Very
by the water to fall.
Yes. Neta 2. Yes. Neta 2 is the viscosity that we want to measure. Rho 2 is the density of the liquid. And T2 is the time taken by the liquid to fall from A to B.
B.
So it is that simple to use capillary viscometer. The construction is simple. The cost is very less because it's a simple glass tube, which is constructed with 2 bulbs on each arm. The procedure cost is also not more. We just use one suction pump. We allow the liquid to reach above level A and we just going to measure. We use stop clock to measure the time taken by the liquid to fall from A to B. So these are all the advantages with this capillary raised viscometer. We do have disadvantages. It cannot measure the viscosities of the liquid where it is more than 40 centipoise. It is almost the viscosity of that liquid paraffin or glycerin, a thickness, something of that sort. We can use it for measurement of viscosity of alcohol, acetone, because those are all the dilute liquids. We can easily use those liquids because they take less time to pass through the capillary. When viscosity goes beyond 40 centipoise, the time taken by those liquids to pass through the capillary is very, very long. You may have to wait for 1 day or 2 days also sometimes, because capillary is very narrow. The liquids are thick. They don't even flow from the capillary. So that is the biggest disadvantage with the Oswald viscometer. So the brand name or the manufacturer name for capillary raised viscometer is the Oswald viscometer. So this is the viscometer which works by the principle of capillary raise. Am I clear?
Clear, Prof.
So that is about the capillary raised viscometer. Any doubts? It is very small, it is portable, inexpensive. You can even have variations in the structure. Instead of making it as a U, you can make even slightly curved and other things. But the basic mechanism is the same. The liquid is allowed to flow through the capillary and time taken by the liquid to pass from one end to the other end is measured. Because this time is purely dependent on viscosity. It cannot measure high viscosity, and you also need transparent liquids, which will allow you to observe their movement. And also another disadvantage is cleaning the capillary tube. Because every time you have to use two liquids. Every time you have to conduct the experiment with reference liquid, and then you are going for the test liquid. So this cleaning is not that easy. Sometimes the liquid may stuck inside the capillary, where the cleaning becomes a biggest problem. And also another disadvantage is that you are not controlling the temperature outside the glass tube. When the liquid is put into the glass tube at midday where the temperature is high, definitely this temperature is going to influence the viscosity, because temperature reduces viscosity. Temperature is inversely proportional to viscosity. When you use the Oswald viscometer at high temperatures, then the values will be less. When the same liquid, same Oswald viscometer, when used at lower temperatures, the viscosity values are going to be high. And always you require a reference liquid. You cannot just go and measure the viscosity of the sample, given sample. You have to always use the reference liquid, because the formula contains viscosity, time taken, and density of the reference liquid compared with the test liquid. So these are all the disadvantages and advantages with the Oswald viscometer. Am I clear?
Yes.
Clear.
We are moving with the next viscometer, which is called as Pauling sphere viscometer. Pauling sphere viscometer is,
Prof,
yes,
uh,
yes.
sorry for taking you back. What do
No.
you say the E1 stands for in reference to the formula?
It is not E, it is rho,
Rho,
density.
density. And then
Rho.
another question, yes, understood. Another question, why is water used as the reference in regardless of other liquids available?
Because water is the universal solvent. It is
Okay.
economic, it is available everywhere, and that is the reason they use. Water is easily available. If you want to use something else, you need to buy.
Okay.
Either you take alcohol or acetone or butyl acetate or ethanol or methanol, whatever you measure, you need to buy them. But water is readily available. And we
Okay.
know all these standard values of water. It is not that it will give only correct values when you use water. No. You can use any liquid as reference and you compare that with the test sample. You can start acetone as your reference also. But in general, water is used as the reference liquid because of its easy availability and because of its inexpensive nature. Is that clear?
What about, Prof? I wanted to also know, is
Yeah.
it also because of the density of water, which is 1 gram per cubic centimeter?
You use any density that is comparable, that is okay. It need not be 1 because water density by coincidence is 1. That's it.
Yes.
No compulsion that the reference liquid that you are going to use must have density 1. No.
Okay, and
Any
then
other
just one
questions?
question. Just one
Yeah.
question about that capillary rise viscometer.
Yeah.
Does the diameter of the capillary tube matter? Does it have its limits so that we cannot be able to use a certain diameter beyond a certain size or a certain that's my question. Like if you wanted to reduce time, would like increase the size of these apparatus.
Yeah, it comes generally from the manufacturer. That's the reason I told you the brand name for the viscometer. So they keep the capillary dimensions in such a way that it can be used up to a viscosity of 40 centipoise. So if you keep
Okay.
too narrow capillary, you may not be able to measure. And at the end of the day, it is the measurement of comparisons, isn't it? For both the liquids, you are using the same capillary. So that is the reason
Yes.
the dimension is not going to have much effect because it's a comparative evaluation, but manufacturer will take care of keeping the dimensions in such a way that liquid flows easily. He's not going to keep it very broad and he's not going to keep it very narrow.
Understood, Prof.
Any other questions? Okay. Can we move on with the next one?
Yes.
The next one is the Pauling sphere viscometer. This Pauling sphere viscometer, you can see the diagram. Is it visible?
No. Yes.
Yes. Yes.
Yellow color stand. So this is a simple glass tube. Can you see a colored glass tube inside this?
Yes.
Yes. It's a big glass jar. Inside, there is a thin glass tube. So this is the actual arrangement. And you can also see a ball which is present inside the glass tube. Can you see that?
Yes.
The outer jar is the water jacket. We have a disadvantage in the previous viscometer. It is prone for changes in the values with the change in the temperature surrounding. So to avoid that, whatever the liquid whose viscosity we are measuring is surrounded with a water jacket and the temperature surrounding the liquid is maintained as a constant value. So we are not allowing interference of temperature during our measurement. So we can see there is an inlet through which the water is supplied. It gets circulated inside the jar and the tube is present inside the jacket. The sample that we are going to add is to the tube. We are going to open the lid which is present on the top and the sample is added to the glass tube. So this is an inlet and there is an outlet also for the water so that water will be circulating to maintain the constant temperature and the whole arrangement can be flipped upside down. So that is the construction of this falling sphere viscometer. Am I clear about the construction?
Yes, Prof.
This whole arrangement is mounted onto the stand so that you can flip it upside down. So that is the construction. Coming to the working. We are not going to use any reference liquid and test liquid. We are directly going to use the liquid whose viscosity we want to measure. It is not a comparative measurement. It is going to work on the principle of sedimentation. We are going to keep the liquid. The liquid is poured from the top. The liquid is filled into the glass tube. Now we are going to add the ball to the liquid. We are going to keep our stopwatch ready. We are going to flip the glass tube upside down. When you flip it upside down, now ball comes to the top of the glass tube, isn't it? Now what happens to the ball?
Comes to the bottom of the fluid, the liquid.
It will start falling down into the liquid.
It hold them.
Yes, it will start falling down. We are going to measure the time taken by the ball to fall down to the bottom. Now, can anyone tell me what is the relation of this time and the viscosity?
If there's the higher the viscosity, the longer the falling time.
Exactly. So it is going to take more time when the liquid is viscous. It is going to take less time when the liquid is dilute. So that is the simple sedimentation principle that is going to be used in falling sphere viscometer. So here we have some advantages. There is no influence of temperature. There is no need of using any reference liquid. It is direct measurement of the test liquid without comparing with any viscosity of reference or density of reference or the time taken by the reference. So that is the main advantage. You have a control over the temperature because of the water jacket that is present, but you do have certain limitations. So the limitations are, suppose the ball is falling down very fast. If the ball is taking less than 10 seconds time, then the results that you are going to get are not reliable. So that is the reason we maintain or we use only those liquids which will take a minimum of 10 seconds to fall down. So that care we are supposed to take when we are using falling sphere viscometer. So we are going to use the formula to measure the viscosity. The viscosity is given with neta is equal to the time taken by the liquid to fall down, sorry, time taken by the ball to fall down, SB minus SF multiplied by a beta. So here, neta is the viscosity. T is the time taken by the ball to fall down. SB is the specific gravity of the ball, which will be provided by the manufacturer, because the ball specific gravity also influences its time to fall down. If the ball specific gravity is less, it will take more time to fall down. If the specific gravity is more, it is
Prof,
attracted.
your screen is static. Could
Am
you
I
please
missing?
repeat?
Am I audible?
No, your screen is not moving, it's static.
It is taking some time, I feel.
We are not able to see the formula.
But you are able to hear me, right?
Yes,
Now
very
we can.
clearly. You can now see the formula.
Yes, it is little lagging. No worries, we can wait. Now you can see the formula, right?
Yes,
Yes, we
Yes.
can see. Maybe just
So
repeat
neta is the viscosity of the liquid which we are measuring. T is the time taken by the ball to fall down. SB is the specific gravity of the ball. SF is the specific gravity of the liquid. Beta is a correction factor. We are going to use a beta correction factor, which is provided by the manufacturer of the equipment. So this beta value is going to depend on the ball, its material of construction, and also the dimensions of the. Because when you see, when we are taking a glass tube, we are adding a small ball and we are adding a bigger ball. Which one will fall down fast? Bigger one or the smaller one?
the big one.
The smaller one.
Exactly. Suppose I'm using aluminium ball and I'm using iron ball. Which one will fall down fast?
The
Iron.
iron ball.
So that is the difference. That is the difference in the material and dimensions of the ball. So by compensating these two factors, they are going to calculate a correction factor, which is provided by the manufacturer, and that we are going to add to the formula in order to measure the viscosity of the unknown liquid. Am I clear?
Clear, Prof.
Any doubts in this?
Repeat the formula.
Yes.
Prof,
Yeah.
you said SB
Yes.
is the specific gravity of the ball.
Yes.
What about SF
Fluid.
or fluid?
The liquid that we filled.
And
We need
B,
to know specific gravity prior to the measurement of viscosity so that we use that value in the formula. And beta is the correction factor, which is dependent on the material of construction and dimensions of the ball that we are using during the experiment. Is that clear?
It's clear, Prof.
Any other questions?
Just one question, Prof,
Yeah.
about the water jacket. It's supposed to have a specific temperature. In this case,
We can even use room temperature. We can use 40 degrees. We can use 60 degrees. We can use 80 degrees. The aim of using water jacket is we are not allowing temperature fluctuations to affect our measurement. In Oswald viscometer, if you could remember, that is one of the disadvantage.
Yes.
So we are not allowing those influences of temperature on our measurement. You use any liquid, one constant temperature, the viscosity must be same. But in Oswald viscometer, you cannot get that because it is completely dependent on surrounding temperature. Maybe today the room temperature is 30 degrees and tomorrow it might be 35 degrees. The same liquid you are measuring today and the viscosity is X, and tomorrow when you are measuring because of the change in the temperature, it is not X tomorrow. You're going to get a new value of Y. Am I clear?
Clear.
So this is 30 seconds. We are going to maintain a minimum time period of 30 seconds. So in order to avoid the errors in the measurements. If the ball is falling down through the liquid within 30 seconds, the values that we are going to calculate may not be reliable. So that is the disadvantage with this falling sphere viscometer. The brand name for the falling sphere viscometer is the Hoppler viscometer. Just give me a second. So just like how Oswald viscometer is an example for the capillary raise viscometer, Hoppler viscometer is the example for the falling sphere viscometer. Is that clear?
Clear.
So these are the two single point viscometers which can be used to measure the viscosity of Newtonian systems. Now you tell me, what is the value of shear stress that you have used? What is that one particular fixed value of shear stress that we are using here? Can anyone tell me? What is the force acting on the liquid here?
Gravity.
Exactly. So gravity is the shear stress that is acting on the liquid. We cannot increase or decrease gravity. It is a constant value. So that is the reason these two viscometers are going to have a single value of shear stress. And that is the reason these viscometers are useful only to measure the viscosities of Newtonian systems. These are not used for the measurement of viscosities of non-Newtonian systems. Am I clear about these two viscometers?
Yes, Prof.
Yes.
Any other questions? Yeah, another disadvantage is it is comparatively expensive than the previous one. Cleaning and maintenance is also little tedious. Now let us have just 2 minutes break and then we go with multiple point viscometers. In the meantime, you can go for the revision of these two viscometers. If you have any doubts, you can just ask me. We'll have just only 2 minutes break, not more than that.
Okay.
Yeah, we can start back. I can see only around 52 students in the class. Hope it is having both the groups, isn't it? Ningisa, please confirm you have some students from your group.
Yes, yes, I have some students from my group.
Yeah, okay. Hussein, can you confirm? Is Hussein in the class? Somebody can confirm from group A.
We
The
do
people are
have,
there.
we do.
Very good.
We are present.
Anyway, the class is recorded. Those who are busy with work and who could not attend the class, they can go for a revision by using the recording. So now let us see the next type of viscometer, which is called as cup and bob viscometer. Can you see the picture here?
Yes, we can see it.
So this is the arrangement how cup and bob will be present. You can see there is a cup-like structure. The outer cylinder is cup-like structure. And now you can see the inner cylinder, which is called as bob. Actually, it is bob, not bob. The bob is attached with a torsion spring so that we can go for measurement of amount of work done by the cylinder when it is rotating. So that is the construction of this cup and bob viscometer. It is going to have a motor which will allow the bob to rotate. Cup is stationary, bob will be rotating. The cup is going to be a stationary part in the viscometer. And bob will be rotating. We do have other model where cup is stationary, bob is stationary and cup is rotating. We can have vice versa of rotations, but the simple mechanism is one of the element will be rotating and the second element will be stationary. So that is about the construction of this viscometer. You can see the same thing here. Here, you can see the bob is rotating. And here you can see the cup is rotating. And the bob is stationary. So coming to the principle of measuring the viscosity, the liquid whose viscosity we want to measure, it is also not a comparative method. We just use only the liquid whose viscosity we want to measure. We are going to load the liquid in between the gap present between the cup and bob. Can you see a small gap which is present between the cup and bob?
Yes.
So that gap is filled with the liquid whose viscosity we want to measure. Now the bob is allowed to rotate, or the cup is allowed to rotate. The speed with which it is rotating is dependent on now you can see the red color which is filled between the gap, and the speed with which the rotations are going to happen is dependent on
Viscosity.
exactly. If the liquid filled in between is dilute, it is very easy for the element that is rotating to show high speed. When the liquid present
Yes.
between cup and bob is thick, that will resist the rotations. Either it is the cup which is rotating or the bob which is rotating, they slow down. The RPM goes down. So we are going to use the formula. Viscosity is given with a constant called as K multiplied by W and V. W over V. Here this is the viscosity. K is a constant. Just like how we have got the beta value by the manufacturer in previous equipment, the falling sphere equipment, K value is also provided by the manufacturer. It's a constant value. Now W is the work done by the rotating element, and this is the speed of the rotating element. The speed is considered in its rotations per minute. So W can be work done, or sometimes we add weights to the rotating element. We go on increasing the weights. Initially, we start with 100 grams. Then we go for another 100 grams. So whatever the amount of force that we are adding is increasing. So these are multiple point viscometers. There is no action of gravity with which rotations are happening. We are using a motor to rotate, and when you add weights and rotate, the amount of shear acting on the liquid is increasing. So as you go on adding the weights, there will be enormous increase in the amount of shear acting on the liquid. So that is the reason these are called as multiple point viscometers. So what is the amount of weight that we have added, or what is the work done by the moving element, and what is the speed with which it is rotating? They are considered in order to calculate the viscosity. It is a simple formula. Viscosity is given with the constant work done over the speed of the rotating element. Sometimes it may be the bob which is rotating or the cup which is rotating. Am I clear?
Yes.
Now the last equipment, cone and plate viscometer. Sorry. I forgot to explain about the advantages and disadvantages with this cup and bob viscometer. So here, of course, we are using multiple values of shear stress. We can use these for Newtonian systems and non-Newtonian systems. We can measure the viscosity at a wide range of shear stress. There is no problem in that. You can gradually even increase the shear stress. All those things are facilitated. But the problem is when you have the cup, which is like this. We fill the liquid like this. And now the bob is rotating inside the cup. So this is what is happening. So this is the liquid. Are you able to see the diagram that I have drawn?
No, we are not able.
No.
Yes.
It will come.
Yes.
Let us consider this is the bob which is rotating and this is the cup which is stationary. So now what happens? Whatever the liquid layer that is adjacent to the bob, because it is the bob which is rotating, the liquid layer adjacent to the bob will receive more amount of shear. The liquid which is present away from the bob, the liquid which is present towards the walls of the cup. Can you see the things that I am drawing here? So this is the liquid which is present near to the wall of the cup. And there is a layer of the liquid which is present near to the bob. So there will be difference in the amount of shear received by these two different layers of the liquid. So especially when it comes to the plastic systems. So what is the characteristic feature of plastic systems? Can anyone tell me? What is the significant difference between the plastic systems and Newtonian systems?
The Y point.
What is that point? Yield point. So plastic systems doesn't show any movement. It doesn't allow any rotations until it reaches the yield point. So already the system is stubborn. It will not allow any movements until it reaches its minimum amount of shear stress. In those cases, what happens? The layer which is away from the ball remain as a solid. It will form as a thick layer because the amount of shear that it is receiving is less. And that shear is less than the yield point of that plastic system. So it doesn't fluidize, it doesn't start flowing, and it will not participate in the movement. So it remains as a solid plug. So this solid plug formation will be always there with the plastic systems. Apart from the plastic systems, even when you consider the shear thinning systems or shear thickening systems, you have a difference in the amount of shear received by the layers. The layer which is near to the bob receives more amount of shear. The layer which is away from the bob receives less amount of shear. So because of these shear differences, sometimes we may end up with errors in the values of the viscosity that we are measuring. To avoid that, the precautions that we are going to take is we maintain minimum gap between cup and bob. When you maintain a minimum gap, you can avoid the differences in the shear stress. When the gap is big, definitely you'll have differences in the shear stress that the layers are receiving. So that is the biggest advantage, and also the sample required for cup and bob viscometer is little large. You may require around 20 ml to 50 ml sample to be filled between the cup and bob. Comparatively large when you compare with the cone and plate viscometer, where it requires only in microliters. So these two are the disadvantages with the cup and bob viscometer. Hope I am clear.
Yes.
The next and the last one comes is the cone and plate viscometer. It is also similar to that of the cup and bob viscometer, only the shapes are different. Here you have seen a blunt bob and a large cup. Whereas here, this is the rotating part. The cone, whatever you are seeing in the picture, the yellow one. So look at this picture. The conical shape one is the cone. And below that, there is a horizontal shape, which is called as the plate. Here, cone is the one which is rotating. Plate is the one which is stationary. You'll have, the plate will be like this. You'll have a small gap to place the sharp edge of the cone. So in this gap, we are going to fill our sample. So now you can just imagine the bob put into a cup, which will be requiring more sample, and a plate and cone, which are exactly fit into each other. The shape is in such a way that there are no dead points. There are no layers receiving different amounts of shear stress, because the small sample required itself is very small. And you see the shape, which is preventing differences in the shear stress received by the liquid. So the cone is placed into the gap. It is filled with the sample, and the cone is allowed to rotate. Again, the same story. If the sample is highly viscous, cone will experience difficulty in rotations. When the liquid viscosity is less or it is dilute, cone will show more amount of rotations. It can easily spin because there is nothing resisting the spin of the cone, because the liquid that was put into the gap is very dilute. But in the same place, if we have the viscous liquid, definitely it will experience some resistance for the movement and it will show lesser speed. It is also going to have the similar arrangement like how you have seen a torque which is fit to calculate the work done by the rotating element. You can see the same part here. There is a torsion spring which measures the work done by the cone. We measure the velocity of the cone. We are going to use the same formula, but instead of K, we are going to use a constant called as C. So it is just a differentiation between the previous formula. Previous formula was neta is equal to KW over V. Here it is C, which is the constant, torque over V. This is the torque or the work done by the cone. V is again the speed of the cone, which is measured in rotations per minute. So this is the arrangement which we are going to have in Brook field viscometer. Have you started doing your practicals?
Yes, we have.
Yes.
Yes, we started.
So whatever the Brook field viscometer that you have seen is going to have the mechanism of cone and plate. It is going to use this mechanism. You'll have different shapes of the rotating element. Some elements are plate-like, some elements are cone-like, some elements are blunt, but the principle is same. It is attached to the stationary element. The sample is placed between the rotating element and the stationary element. Depending on the viscosity of the sample between the elements, you will have the rotations of the rotating element. If viscosity is more, rotations will be less. If viscosity is less, rotations will be more. So that is how we are going to have different viscometers even here. You can increase amount of work done by this by adding weights to the machine. Everything is present inside. So as you are increasing the shear, as you go for the second level, third level, and fourth level, the weight that is going to act on the rotating element will increase. So which will increase the shear stress transmitted to the liquid so that you can measure viscosity at different levels of shear stress, which is required for the non-Newtonian liquids. Either it is the plastic system or pseudoplastic system or the dilatant system. Am I clear about cone and plate viscometer?
Yes, Prof.
Yes, we are.
Yes.
Any questions? Cone and plate viscometer will have direct reading of the viscosities because it is automated already. It will calculate this formula and it will directly give you the viscosity values. And it is very easy to operate because you'll directly have those shear values and the RPM that it is going to use. And it will also directly give you the digital output of the viscosity. And the sample required is very less because the gap present between the cone and plate is very small. So with only milliliters of the sample, you can complete the measurement. It can be used to measure the wide variety of viscosities. It is not restricted to lesser viscosities or it is not restricted to higher viscosity. You can measure wide range of liquids with wide range of viscosities. Any questions?
Any disadvantages?
Expensive. Definitely expensive, and it also requires prior training to operate. You cannot just go and operate it like how you use Oswald viscometer. It is very simple. You add liquid, you suck. But here, you need to understand the equipment, you need to understand the inputs, you need to understand the outputs. Then only you will be able to operate this equipment. Expensive, and it is not that easy to operate. Any other questions? You can ask me whether temperature is influencing the measurement here. Is it influencing? Like it doesn't have any water jacket, and it is not having any control over the temperature, surrounding temperature. But the equipment directly gives you the viscosity at the recorded temperature. Equipment knows the temperature where it is measuring the viscosity. It will give you the viscosity at definite measured temperature, so that you don't have any errors. When it is measuring the temperature, it will give you the respective viscosity. The same thing is applicable for the cup and bob viscometer also. Any other questions? You can just go through all the 4 types of viscometers and just let me know if you have any doubts or any repetitions to be done. Just take 5 minutes. If you have any questions, I'll answer the question. Otherwise, we can close the class. Just take 5 minutes. Go through your running notes or go through whatever we have discussed until now. If you have any questions, you can ask me. This is a makeup class for the upcoming Thursday that I'm missing. I would like to go for one more makeup class next week, Monday, so that we'll be moving ahead with the syllabus. I'm not missing next week, Thursday class, but still I want to take one more makeup class. Hope this online class is okay on a Monday.
Yes, it's okay.
It's
Very
very
okay.
okay. Very okay.
So we are meeting again next Monday also. In the meantime, you can
Yeah.
search for your clarifications. Any questions in today's class?
Doc, we have a request. Will you please help us with the notes? Because some of us are at work. We have not been able to copy the notes.
No worries. If you don't have any questions or the clarifications to be done, can we close the class?
Okay.
That's okay.
Yes, Prof.
Thank you very much for your cooperation. I really appreciate. I know how busy you people are, but still, thank you very much for your cooperation. Thank you.
Thank you very much, Prof, for the lesson.